You very informally last week, nodes that send messages. But here we actually want a formal model, mathematically defined, because we want to be very precise in this course. Then I'm going to talk about executions of the system and computations, which is not the same thing. After that, we'll talk about causal order. Causality is the most important concept in distributed systems. It tells you what you can do, what you cannot do. Then we'll give a theorem on this called the computation theorem, which tells you something important about computations. We'll talk about clocks. So basically, clocks, it's not like a clock, a wristwatch or something. A clock is a way to count events in a distributed system and to determine causality. And if we have time, I'll talk to you about the complexity paradox. So we'll talk a little about complexity, which is the number of messages or events. Okay, so let me introduce a little bit, give an overview of what I'm going to say on the board. First of all, in the formal model, so modeling is what scientists do. They take the real world, which is complicated, and which one can say is even infinitely complex. People think in science that we understand the real world. Physicists, they have this twist in their brain. They think they understand the real world, okay? They build large hadron colliders, billions of euros, but in fact, there's many things they don't understand. The world is infinitely complex. So the way to solve that in science is to make a simplified version, which is called a model of the real world. The model has to be complicated enough so that we can actually use it. So it has to be complete, which means that we have to be able to say, to do strong things, like for example impossibility proofs. It has to be able to say things, impossibility proofs. It has to be strong enough that we can actually do something with it and prove things, like certain things are impossible, okay? It's a little bit clearer with the slides, I think, yeah? So we're going to do formal models. So first I want to give you kind of an explanation of what is a formal model. So you take part of the real world and you abstract it, okay? Which means you make a simplified version that still respects the real world, we hope, huh? That's the point, huh? Never really sure. So the real world is infinitely complex, and we make a simplified model, okay? So modeling is the foundation of science, okay? What can modeling do for us? Everything, okay? Solve problems, build systems, understand, analyze. So modeling is super important. So you already have learned modeling. Okay, there's two basic kinds of models. The discrete event models and continuous models. A lot of people in the engineering EPL, they love continuous models. So this is typically differential equations. So I'm sure you all have had lots of very beautiful courses on differential equations, and you love this, and it's a great approach, and you dream about differential equations. Okay, so in this course we're not going to do differential equations at all. We're going to do another kind of model, which is a model that normally you have not seen so much, okay, which is a discrete model. State transitions, no continuous variables, almost none. It's completely discrete. So that's a really different way of doing models, okay? So we're going to do discrete models in this course. So you're going to learn some nice discrete models. So how do you pick the right model? So the trick is the right level of abstraction. You don't want too much detail or it's too complicated, but you don't want it to be too simple or else you can't do anything. You can't do anything. So you have to have enough power to show impossibility proofs. That means you have to be able to show that something is impossible. Like we saw last week, the two generals problem is impossible, so agreement, consensus, is impossible in an asynchronous system where if any node can fail, if you can have at least one failure, it's impossible. And you can prove that, and there's a mathematical proof. So that means asynchronous systems are very hard, okay? So this, we will do this. But still, you don't want the model to be too complicated or else you spend all your time fighting against the complexity. So there's actually three properties. One is that it has to be powerful enough, and we say it has to be complete, not powerful. The second one is it has to be correct. That means it has to respect reality. It has to do right things and not wrong things, okay? No mistakes. And the third thing, it should not be too complicated, okay? So that's a different kind of property, yeah? So it has to say enough, not make mistakes, and not be too complicated. So okay, so that's the general idea of modeling. So I'm going to show you a model of distributed system today that is one of the simplest you can do for distributed systems, but you see there's a few little things still that are not that simple. Okay, so we're going to model distributed systems. So let's start from the intuition. You have a set of nodes connected by a network. So they're sending messages, and they're solving a common goal. That means there's one algorithm running on all the nodes, okay? So how do you model that? Well, we're going to do in two steps. We're going to first model one node, and this is something that you already normally know. This is a kind of state machine, okay? And then we'll model how the nodes are connected, the network. So the modeling the network is what makes it a little bit more complicated. So what's the simplest way of modeling a network? We don't want to model TCP. We don't want to model IP. That's already very complicated. So how do you model a network so that it's simple and still powerful? Okay, so we're going to see that today. So first I talked about one node. So one node is actually fairly simple, but not so simple still, okay? Because the node has two things. It can do, of course, local computation. It can compute, it has its local state, and it can compute with that. But it can also send and receive messages, okay? So this send and receive messages is a new thing, is an extra thing, okay? So we're going to model nodes by like a state machine. So this is called a state transition system. There's many ways. You have already seen state machines. So it's very similar to finite state machines. You have a state and you send a message and it goes to another state. You know, very simple, but it's maybe not finite, okay? And there's really no input. I mean, there's messages, but that's all that there is. So you have a set of state and a set and a function. So basically a transition function. So a function that goes from state and message to the next state. Okay, so you have a set of states. Let's say whatever, S, and then you have a transition function. Okay. Okay, F, which goes from a state and a message, and it goes to another state. Okay. Also, it has a set of initial states. okay, which is a subset of the total set of states. So that's it. So this is very simple. I'm not going to say so much about this, but we're going to use it all the time. So all the programs you run are doing this, okay? So here's a little program written in some weird pseudo code. X gets 0 while x less than 2, do x is x plus 1, and then you find x equals 1. So you have states here. So here each state is just the value that's in the variable x. So the state is just all the values in the variables, okay? So there's a number of states here. There's a transition function. So once x gets 0, then the next state will be it gets 1. That's incremented. Then it gets 2, okay? And then you go out of the loop, and again it gets 1, but you're in a different state because you're at the end of the program, okay? So that's the state transition, okay? So that's very simple. It's just a state machine. Now I'm going to add something to this because of the distributed system. So you have the state machine, okay? And I just showed you an example, which is the local state of the node. But you have something extra, which is the network, okay? So here's a node, P2, and we assume that each node is connected to a set of neighbors. So here we have P2, maybe it's connected to P1, P3, and P0. So these are the neighbors. So we're assuming that there's some graph, okay, connecting the nodes. So we're not going to worry about routing at this stage. We're going to assume that the node can only talk to its neighbors, okay, to keep things simple. And how do we model messages traveling through the network? Because what happens in a real system? So I have a program, I send a message. I do send or something. The message disappears from my program, and sometime later, it magically appears on the other side, okay? So we're going to model this. So this is a complicated process. There's lots of code doing this. And then you have all things like packets and timing and whatever. So we're not going to model all that. We're going to model it in a very abstract, simple way. So each neighbor has on each of the lines, on each of the network lines, it has two sets, an in buffer and an out buffer. So sending a message means putting the message in the out buff for that line. And receiving a message means taking a message out of the in buff. Okay? So, and then there's some magic that causes the message to go from an out buff to an in buff. So here's an out buff, okay, for node 0. Here's the in buff coming from node 2. So if I want to send, I put a message in the out buff locally, and that's my local state, okay? And some magic rule causes the message in here to disappear here and to reappear there. Boom, by magic. That's part of the model. The model is you just assume it's magic. The message appears there, and then the guy can take it out and do local computation. So we're not worrying about messages traveling or even failure at this level, huh? Not yet. Huh? We're not worrying about encoding of the messages. We're not worrying about routing. We just want something to get from this node to that node in a simple, formal way, okay? So that's how it works. So we have local computation, which is just state machine turning around. And then we have an extra magic rule that causes messages to jump instantaneously from out buff to in buff, okay? So that's how it works. So that's it. So that's very simple, right? It is a simpler, much, much simpler than the actual network, but it's strong enough nice that we can do a lot with this. And of course, if you do TCP, whatever, you implement stuff like that. But we're not going to worry about that level. That is the problem of Olivier Bonaventure. It's not my problem. He loses sleep on that, not me. Okay? Which is true, actually. So here is an example of an execution. So this is one node. So I'm still looking at one node here. This is the node, which is number P2, which has 3 network connections. 1, 2, 3 here. I number them. 1, 2, 3. So it starts the local variable. So the x is the local variables, huh? It's starting at 0, and all the sets are empty. Okay, now I'm doing computation. Okay, so right now, so far nothing is doing, but somehow a message magically appears in the in-buff. Oh, nice. Okay, so that makes a transition, huh? The message magically appears on the in-buff. Nothing else has happened. But the node will see that. So the state of the node, which is all of this, changes. So now I have this extra piece of state, and the in-buff I can read it. So what happens? Now I'm going to do local computation, which means I take M0 out of the in-buff, and then I update the state. So there's only 2 ways to update the state. I can update local variables, and I can put messages in the out buff. Maybe, okay? So in this example, the state becomes 1, and I send one message, M1, on out buff 1. Okay? It's just in the example. So I'm reading M0, and I send M1. Okay? Now, notice I have not shown you the magic of how this one appears. It just magically appears. Okay? So let's go on. So I'm here. Okay. So this is still the same. Huh? So this outbuff message is still there. Because there has to be a magic rule that some other node takes it out and it becomes empty again. But so far it stays there. But another message comes in. So inbuff 2 has magically gotten M2. Okay. Fine. But this is a state machine. So there's some non-determinism here. Huh? So here another message comes in, M3. So far I have not done any transition yet. Huh? And then I take both messages out, so inbuff 2 becomes empty. I do a computation, so I change the variables. And in this case, I'm also sending a message. So you see how it works. Huh? Messages magically come in on the inbuffs, and the state transition function knows about that. Huh? And then it does something, and maybe it sends another message. So basically, in the node point of view, sending, it just means put in the out buffer. And the receiving messages, they appear magically. Okay? So you see how it works, huh?
Excuse me?
Yes?
How do we decide if we treat 2 incoming messages? Why is it 1 state changement and not 2?
Ah, so there's some kind of a non-determinism here. Huh? So the messages are actually coming in, so it's interleaved. So I can do local computation, but messages can come in also. Okay, so I have 2 possibilities. So in fact, I don't really know. Maybe the messages, I could have actually done a local computation here. So this is a source of non-determinism. So I have a choice. Okay, so here I choose not to do anything right away, and then somehow another message comes in. So I have transitions, okay, events. But the events can be messages arriving and can be local computations. There's 2 kinds, huh? It's the magic events coming in or the local computation. So there's non-determinism between those, okay? So that's a source of non-determinism, okay? Because it's models. So why do I do like that? Because that's how the real world works. If I receive a message M2, then maybe the local machine does not execute right away. Maybe another message comes in and then it executes. That's possible, right? There could be a local thread, or maybe the network buffer is actually receiving 2 messages, or maybe it does a local computation after M2 and then another one when M3 comes in. So both situations are possible in real life. Huh? So the reason why it's non-deterministic, it's not because I'm a masochist or something, because non-determinism is a pain. It's because the real world is like that. So I kind of am forced to do it like that. Huh? Okay? Is that answering? If you're not happy with my answer, complain. Huh?
It's my question more precisely is
okay.
that for the last changement.
Which one?
From x1 to x2.
Okay, this one.
Yes, we treat two messages at once.
Yeah, so that's the model 2. So yeah, why are both messages taken out? Well, in the that's to simplify the model a little bit. You empty the in-buffs, so you basically take both messages into account. But there's, I mean, yeah, that's kind of a choice. You could also do one at a time. That would be a small, different model, but it doesn't change anything profound. Because you can always model one or the other. I mean, you can always assume that there's some intermediate step or something. Yeah, so when I empty the in-buffs, I'm completely emptying them, in fact. Yeah. So you can see that this model is a little bit arbitrary, so you can do lots of variations of it. So what I'm telling you is not like a divine illumination or something. So God told me that this was the right model. And if you don't use this model, you're a heretic, and we will burn you on the stake. No, it's not really like that. The only thing is that this model is actually a good model because it works. So the other model, the other variation also works, where you take only one message out at each time. But there's really no difference because you could easily formulate one in terms of the other. Okay? Okay, so you see, you're getting an intuition on this model. You see, it looks complicated, because each of the network connections has this in-buff, out-buff thing, okay? Out-buff, in-buff. Because the messages will be bidirectional. So we can assume between two nodes that the messages could be going both ways, always. This model is like that. If you have a system where it's only one directional, well, you just assume that there's nothing ever coming in, okay? But in general, if you have a wire connecting two nodes, in real life, usually it's going to be bidirectional, okay? So here also, it's bidirectional, okay? So you can see there's lots of arbitrary choices, and it's kind of driven by the model has to work in the real world. So we're going to do proofs on this with this kind of model, and the proofs have to be strong enough that the real world is, when we prove something is impossible, in the real world it should be impossible also, okay? So the model has to be kind of respecting the real world. Okay, so we have a little bit of terminology. All state except the outbuffs is called accessible state. So the variables and the inbuffs, that's all what's stored there. In fact, the outbuff, once I put a message in the outbuff, I cannot read it anymore. The message is gone. It's in the network, okay? So I'm assuming that once I put something in the outbuff, that I cannot read it anymore. I mean, I see it here, but in the model, the transition function will never be able to see this, okay? Of course, I can see it like here, it's there, but you see the model is not as smart as me. It cannot see this, okay? And so the intuition is, when I do send of a message, it's in the network, and it's traveling in the network. It starts by going into the operating system, goes into the network layers, then stuff happens on the wires, it goes maybe through routers, it's doing all kinds of stuff, but it has disappeared from my local machine, okay? So when in the outbuff I cannot read anymore. Also, the inbuffs are read-only. So that's logical. When a message comes in the inbuff, I can read it, but I cannot change. Doesn't mean anything to change it, okay? It's the message that comes in. So in the model, that's the message coming in, and that's it. I cannot change it, okay? So that's how the transition function is defined. It takes accessible state, so everything except outbuffs, and returns new state. It sends messages. It will add at most one message to each outbuff. So why one? That's kind of arbitrary. I mean, if you want to do 2, you will have to do 2 steps. It reads messages. All the in-buffs are empty. So that is actually, if we're making it somehow simple, once you do a transition, the in-buffs are empty again. Okay? So it reads all the incoming messages, but it only sends 1. Why it's like that? Well, you can do variations. But if you do like this, it makes things a little bit simpler, that's all. Okay? So you see how it works, huh? So the out-buff, in-buff is a little bit subtle, you see, huh? Okay. So there is a formal set of constraints on the transition function, which is on this slide, which looks very complicated, but I'll explain. So it's actually intuitive. But basically, we're not going to worry about this so much. So I have to explain it once, but then you'll see later on we don't really have to worry because it's somehow automatic. But when I'm defining out in-buffs, I have to make some formal definition. Okay? So the state of a node with k channels is a triple, IOS. So I is a vector of in-buffs. So each line has an in-buff, huh? O is a vector of out-buffs, huh? So each of these lines has an in-buff and an out-buff, huh? And S is the local state, which is just the variables, the local variables. And then there's correctness condition. So assume we have I1, O1, S1, and F is transition. So this does I2, O2, S2. But assume we have another one, I3, O3, S3, and it does I4, O4, S4. Now we can make some conditions, okay? So first of all, I2 and OI4 are empty. Well, basically, vector of empty sets. So all the in-buffs are empty. So this is just the rule that you read all the incoming messages, okay? Then there's determinism rule. If I1 is equal to I3 and S1 is equal to S3, then S2 has to be equal to S4 because the transition function is deterministic, but only on the accessible state. Huh? Notice the O's don't make any difference here, okay? So S2 is equal to S4, that means it's deterministic function on the accessible state. And then there's some funny conditions on these O's. So O1 is a subset of O2, and O3 is a subset of O4. So what that means is I only add messages to the out buffs. I'm not allowed to remove any, you see? Or I add none if it's equal, or if it's strictly subset, I'm adding a message. I can only add messages to the out buffs. So that's a rule. That's clear, huh? That you can only send, once you send something, you can't retract it. And the other thing is O2 minus O1 is equal to O4 minus O3. That means O2 minus O1 is the messages that were sent here. And O4 minus O3 is the messages that were sent. It's the extra messages. Sorry, no. O2 minus O1 is the old messages. Sorry. Wait, am I doing this? Yeah, so the messages sent here are the same in both cases, huh? Okay, and yeah, I say outbuffs keep their old messages. So when the execution is going on, that you're always adding the same messages, okay? So this is the formal definition, but it's just a way of making the intuition precise, okay? So this definition, which I did not invent, it comes from a book on distributed systems, which is a famous book by Etienne Welch. The book actually has a small error in this definition, which just goes to show that formal definitions are not easy, even for professionals, okay? So these two people are very well-known researchers in distributed systems, but in the book, if you look at this book, you'll see that there's actually small errors, okay, in the definition. So that's okay. So this is, I have to show you this, but it's just making the intuition precise, okay? Okay, so now let's get back to something more intuitive. So the node is executing, okay? I gave you already an example, huh? So how does it work? So each node is just doing a loop. Huh? It waits for a message. When message comes in, it does a local computation and it sends more messages. Of course, respecting the constraints of the transition function. Huh? So when a message comes in, it does, it's a transition function, it does something. It might send more messages, okay? Actually, so it's more like this, huh? This is reading from the in buff. So this is actually more precise. So this is going to the out buff, huh? And this is actually a set of messages, and there's some more constraints. There's only one message per out buff here, right? So this is kind of an approximation of, there's some constraints on this function, which I showed you. But the precise constraints are not really very important, and if you don't say them right later on, I will not really penalize you for that, because there's many variations. Okay, so this is what a node does. Okay, that's very simple, right? Okay, right? What do you think? It seems very simple, huh? But I want you to be skeptical. So is this good? Is this reasonable? So D means I'm asking now for you to give me some input. So is this model reasonable for one node? Huh? For one node. What do you think? Maybe it's bogus for some reason, or maybe it's fine. So is it deterministic? Is it? Well, the transition function, I told you, it's deterministic on the accessible state. Huh? So it is deterministic, yeah? Okay. I told it to you already, on the accessible state, because you cannot read the stuff you sent. So in terms of the messages coming in the state, it's deterministic, fine. But a real distributed system is non-deterministic, of course. So if this is deterministic, where's the non-determinism in the distributed system? Of course, a real distributed system is non-deterministic, because in an asynchronous model, you don't know how long the messages are going to take, and things, if you run the same program more than once, it can do different things, depending on the timing, okay? This model should have that property too, right? If we want it to be a good model. But the state transition function is deterministic. So where is the non-determinism? You tell me, where is it? Yes?
The moment where we receive the message?
The moment we receive the message, that's very correct. Yes, that's exactly right. So, in fact, this is only the local computation now. I still haven't told you the magic rule for messages coming in. But the magic rule that transfers a message from an out buff on one node to the in buff on another one, you also need that, in addition to this. And this transition, you can do it anytime you want. You don't have to do it immediately, okay? So the non-determinism is in the messages, is in when you receive the messages. That's the only place, yeah?
In step 2, can the smaller steps be done in a different order? Like, can you send messages and then do local computation?
No, I mean, in this model, it's always like this.
Okay. But would that make a difference?
What would be a different model? But it would probably, if you vary this a little bit, it would probably not make much difference, okay? There's many possible ways to model a distributed system. But this is actually very reasonable. I receive a message, I have my local variables, I compute, and I might send another message. That's reasonable. So this actually is a very reasonable model. It's very intuitive. I receive a message, I do local computation using the message and the local variables, okay? And then I maybe send more messages. Some messages on the out buffs. Well, could be 0, maybe I send 0 messages. But maximum 1 per out buff, okay? That's very intuitive, huh? So, how is I/O done? Okay, so this is kind of a weird question. Computer systems have I/O, okay? Well, how would I display something on a screen? This doesn't really do that, or print something, or store something on a disk. Well, that's not actually modeled here, huh? I would need some kind of special node that handles it. This is all, everything is done here through messages, okay? So this does not really model I/O. Huh? So what about, is the execution of one node atomic? So what does that mean? You should know what that means, huh? Is this each execution here atomic? I mean, atomic, which would mean what exactly in this case? Can you tell me? What would that mean here? So each node, is it executing, doing atomically? Yeah?
It will always be in one state and not be in something that...
Yeah, it's always in a particular state. A message arrives, and then it goes to another state. And in fact, we never see the intermediate. So this might be long computation, a very long one, but we never see this computation because we only wait for a message here. We're never going to interrupt this computation. Huh? So if this might take a long time, but we'll only wait for the message when the node decides. So this is atomic. Huh? We will never see an intermediate state. We will only see actual states of the transition function, huh? Even if it's a long computation. So it's atomic. Huh? The nodes are doing atomic transitions. Okay? Okay, so you see that's all one node. Huh? Now let's go to many nodes. That's it for one node. We know how it works now. Huh? The out and the in buff. Now let's look at many nodes. So first of all, I need to introduce a terminology, a word. So each node has a state, right? So this is the state of a node. But this is a distributed system with 3 nodes. So in fact, in distributed systems community, we don't call this the state of the distributed system. We don't use the word state for the whole system. We call this configuration. And the reason is purely to avoid confusion. If I'm telling you the state is this, then you know I'm talking about one node. If I'm telling you the system is in this configuration, you know I'm talking about the whole distributed system, okay? So the configuration is actually the state of the whole distributed system, okay? So one way to remember that is state is a very small word, so it's a small thing, whereas configuration is a big word, so it's for big thing, okay? Okay, so this is just terminology, but it's important because we're going to talk about configurations a lot. Huh? So configuration is always basically a vector. It's a vector of the states of all the nodes in the system. So Qi is the state of node Pi. Okay? So it can be huge, huh? And nobody knows it. So P1 does not know the state of P2 and P3, yeah? Whereas P1 knows its own state, it will not know the other states. So normally, nobody inside the system will know the configuration. Only when we reason about the system, we have like God's eye view. I'm looking at the whole system. But inside the system, normally nobody will know the configuration. Okay? Okay, for the terminology? Okay? So then you have initial configuration, is where each Qi is initial state. So when you start up the system, okay? Okay, so this system is now going to execute. So how does it execute? Well, this is kind of like a concurrent system, huh, with many threads, huh? Remember? So each of these nodes is actually doing like sequential execution, huh? You can see that it's doing a sequence of transitions. So this is kind of like a concurrent system. It's a little bit more because you have a network. So we're going to make it execute by what we call events. So event is something that makes you go from one configuration to the next. Okay? There's 2 kinds of events. So there's a computation event, and then the magic transmission, which is called delivery event. Okay? So there's only 2 kinds of events. So I already showed you what this is. Huh? This is the local transition, huh? According to the function f. And the delivery event is the magic transition of a message from out buff to in buff. So that's called the delivery event. Okay? So it's a single event. And in the semantics of the model, it's a pure instantaneous atomic transition, okay? So that's how we model the time. We have a sequence of configurations separated by these two kind of events, okay? So computation event. So to make it simple, there's actually a state for the whole configuration, huh? But let's just say comp I. So when we don't want to say all the details, we'll just say node I does one computation event, comp I, okay? So this applies a transition function on the state of node I. So that's one thing happening on one node. And the delivery event, that's this magic thing. You move a message from the outbuff of PI to the inbuff of PJ, okay? Message N goes from I to J. So this is instantaneous in the model. Okay, so we're not modeling all the hard work of my esteemed colleague here at all. We're assuming it's a trivial thing, okay? I don't think you would mind, okay, that we do that. Because we're going to build on top of it. We're going to build many algorithms. So the underlying network layer, we reduce it to this. It's just a simple transition here, okay? So all the complexities that you saw in your networking course, it's this, one line, okay? Because we're building on top. So we abstract it away. And actually that's a compliment to the networking guys. The fact that we're able to abstract it away like this means that they do their work right, huh? That we can make it look so simple. That means it's actually a good abstraction, huh? So now we have an actual execution. So now we finally get to a running distributed system. So an execution is this thing. So an execution is this letter E. It's an infinite sequence. And it alternates. You have a configuration, so it starts in C0, you have an event, another configuration, another event, and so on. You could write it in a slightly different way, huh? You could write it like this. Let me make a picture. You could say this also, huh? It's just a notation, huh? So you could write it like this. Sorry, this starts with E1. So the C0 configuration, you have an event, E1, which is either comp or del. And then you get another configuration. And then you keep going like that. And it keeps going forever. So that's an execution. So most of this course, we're going to be studying the properties of this thing, huh? Okay? So all our complicated algorithms, synchronous, asynchronous, consensus, broadcast, whatever, it will all be just variations on this sequence, okay? Okay? So let me just explain a little bit more in detail what it's doing. So if the event is a comp event, then what happens is ck minus 1 will change to ck because it will apply pi's transition function on the state of I in configuration k minus 1, in ck minus 1. Huh? So that's what this comp I means. Huh? Comp I means that pi is doing a local computation. And it's doing what I explained here. Huh? So it's reading all the message from the inbuff, it's using its local variables, and maybe it's doing some sense by putting stuff in the outbuff. So that's all one thing. Huh? Okay? So EK can be comp I. It can also be a del. And those are the only two things. Huh? There's only two kinds of messages, two kinds of events. Huh? So the del for delivery. Yeah? So if the event is a del event, then the configuration changes by moves m, I already explained before, from i's outbuff on the link ij, yeah? So j is in buff. So the message hops from one node to the other, like that, instantaneously in our model. Huh? So of course in the real system, this one little thing can be very complicated. Huh? If I do HTML, HTTP, back and forth, one message going from one to the other, there's a lot of code running, but in the model it's just this, okay? Because in the model we abstract all that away and we have just that, okay? So this is the thing we're studying in this course, huh? We're actually studying the properties of these things, these executions, okay? You can write them like this if you like, with arrows, but it's the same, huh? You can see it's very similar to a concurrent system, huh? If you followed my course or other course on concurrent, on languages with many threads, the configuration would be then the state of all the threads, and then you would have, this is an interleaving semantics. Remember in concurrency we talked about interleaving semantics? So in each step we're only doing one thing. So if 100 nodes all compute, this is going to be 100 steps in this model. Huh? Each step is one node doing one thing. Okay? That's important because that makes reasoning much, much easier. There exist models which is called true concurrency, where you can do many things in one step. It's way more complicated. But some researchers say, yes, but this is real concurrency. Well, maybe, okay, but it's much more complicated. And in fact, it doesn't change anything for what we're going to do in this course. Okay, so here's an example of a system, simple one, huh? So this system has 3 nodes, P1, P2, P3, and 2 network connections between P1 and P2, P2, P3. So here I have P1, P2, P3, the 3 states. So this is my configuration C0, okay? Here I've actually put some messages in the initial system. Here I have a message in M1, outbuff, and then here also a message M7, okay? So what do I do now? Well, there's no messages in the in buffs, okay? But I could do a local computation, huh? You can do local computations with no messages in the in buff sometimes. But in this case, you will not do that. So the first event here is a delivery event. M7 goes from 2 to 3. So this M7 here will move to P3, the in buff, and this out buff goes empty. So these 2 red things are the only pieces of the configuration that change. Huh? Okay, and then I do comp 3, so I do a local computation of 3, so the in buff becomes empty, the state changes to 12, and I'm actually sending another messages on the out buff. So these 3 red things are what changes. So you can see that a comp event will only change state on one node, and a del event will change the state on 2 nodes, okay? And there is no event that changes instantaneously the state on 3 nodes. That's not possible. That's according to physics. You can't really do 3 things. I mean, you could maybe model that, but there's no reason to model that. So these are the only 2 kinds of events that change one node and that change 2 nodes. Okay? Okay. Let's, maybe we make a small break now, because this is nice. Now we know really how a distributed system executes, okay? So look at airline. In fact, it's very easy to look at study airline. So let me explain to you. So the main site for airline is airline.org. And you can go there and you can download the system and you can immediately start using it. And then there's a lot of documents on Erlang. There's lots of ways of learning Erlang. But one of the best is a website called Learn You Some Erlang for great good. Huh? That's a nice name, right? So there's a site, if you type this in Google, you will find it immediately. So this is very pedagogical. It starts very simple, has many examples, and there's even a book that you can buy if you want, but it doesn't cost anything, the website. So if you want to already learn something about airline, this is a really good way to get into it. Okay, and it explains progressively the things you can do, and the airline system is an interactive system. It has an interactive top level. So you can immediately type expressions and do things right away. Of course, you can also write huge programs and files and make files and whatever, huge millions of lines, but you can also just try out things. So it's actually a very easy system to start using, okay? So you can download the latest version here, and then you can look at this. Of course, there's much, much other documentation and things. There's a huge amount of stuff on airline on the web. So this is by far not the only things, but these are a good way of starting, okay? If you want to take a look. So we're going to do the project of the course in airline, and actually, it's actually very natural because airline, the model of airline is very similar to the model we use in this course. It's messages between processes, so you have send and receive, and you can do, it's very similar to the pseudocode we're going to use in this course. And it's a system that's very easy to use. You don't need to do a lot of baggage or boilerplate, okay? Airline, you can start very easily. So you can do very nice projects, and you can implement the algorithms in this course in a fairly simple way in airline, many of them. So it's a good language for that kind of thing. So that's what we're going to use for the project. You don't have to learn it right away. We're going to organize a few lab sessions which will teach you enough about airline so you can do the project, okay? So there will be a few lab sessions on airline. But if you're interested in looking at it now, please be my guest. It's actually really nice. Erlang is actually a very powerful system, okay? So I welcome you to look at it now if you want. But you don't have to, huh? Okay, so let me continue. So this is an execution, okay? Okay, so now let's just make some. So you see how it works, huh? Configurations, they do steps with del and comp events. And the magic messages are transmitted through this del transition from out buff to in buff. That's it, huh? That's the model. So it's not really that complicated. I'm going to introduce a little bit of terminology. So, okay, each comp event has a transition, of course, huh? So when I say comp I, it's just like a shortcut, huh? Because there's actually a transition with a beginning state of a node I, which has, starting from this state, goes to this state, node I. So this is the transition. And there's also some notation. We say the transition is applicable in configuration C if the accessible state of node J is S1. So basically what that means is, it's actually a very simple idea. So if this is a comp event, comp I, there's some transition. All that means is that the S1 is actually the same state. This is actually the states of all the nodes. Huh? The C is actually a vector of the states of all the nodes. When this event works on this configuration, of course, the state S1 of this comp has to be the same as the state S1 in the configuration. Otherwise, it doesn't work. Huh? It has to fit. So that's something we say it's applicable. Okay. So of course, it has to start with the state that's in the configuration. And it's the same idea for the delivery event. So del IJM is applicable if in the configuration C there is an M in the outbuff for the link, in the link IJ. Okay? Otherwise you cannot do the del. Okay? So that's kind of reasonable, huh? So that's a word that's sometimes used in technical papers and so on. So I just mentioned it. Okay? So here is, we make kind of a microscope on the comp event. Okay? So here I have a very simple system with 2 nodes, configuration of 2 nodes, and I'm doing comp2 event. So this comp2 event actually corresponds to a transition, okay? Usually I don't say it because it's kind of heavy to say it all the time. But when I do comp2, it's clear that there's a transition, so that I'm looking at the process P2, okay? I'm looking at the accessible state, so X is 11, in buff 1 is N7. And then on the other side I'm actually creating an out message in the out buff, okay? M8, and I also have the 12 and the in buff is empty, okay? So there's this transition of the states. So usually I'm not going to say that there's a transition connected to comp2. It's enough to say comp2, and you know there's a transition, okay? Just to put a dot on the app, okay? Okay, and then, another thing. So sometimes there's a function called app apply. It's kind of apply. So basically, app of E1, C0 gives me C1. So basically, the app is following one arrow, okay? So app of E2, in this case, C1, gives me the resulting configuration, which is C2. So this is another kind of notation. Not very important, I mention it like that, okay? Okay, now let's study a little bit more these executions, okay? Execution. So let me write down first an execution. So C0, E1, C1, E2, C2, E3, and so on, huh? So it's this sequence. So let's take a look closer on this. Okay, so nodes are deterministic. Okay, I told you that already, huh? Given a message, you update the state, you send some messages, and it's always deterministic. If I have the same message coming in and the same state, it will do the same thing, always, okay? But the messages, the del events are actually non-deterministic, okay? So this is the asynchrony. That means if there's a del in here, del 3, 4, m, for example, I put it here, for example, but I don't have to do it there. Maybe I do it later. A message, I put it in the out buff, maybe it stays a long time in the out buff, and then I do del. So the del doesn't have to be done right away, okay? Messages take arbitrary time, and what that means is that the del, which is what transfer the message, huh? The del, it doesn't have to be done right away. It could happen a long time later, okay? So that's actually the same as an asynchronous model, which I mentioned last week, okay? Which means messages are arbitrary time to be delivered. In this model, there is no limit on how slow the del is, okay? It can be thousands of events later that you do the del, or 10,000 or a million or whatever, okay? So the del's is, there's no constraint on how long you wait to do a del in this model, so that makes it asynchronous, okay? Okay, so that's one thing. So the sequence of events is actually very important, E1, E2, E3. So we're going to look at that separately. Forget the configurations. Let's just look at the events, okay? This is called a schedule. So let's just look at the events now. And you can see this is important because a del event you can make it very late in the schedule, okay? So we're going to talk about schedule, okay? So you can see each event is either a del or a comp, okay? The asynchrony is purely determined by the del. Where are the dels? Maybe I'm doing lots of comps, and the del, I push them, I'll do them later, fine. So basically, the schedule is a non-deterministic thing, okay? I can do the same computation, but the dels maybe are very slow, okay? The comp, another thing, is doing a local computation. But I don't tell you how long it takes, okay? A comp is any local computation in this model, okay? A comp event. Maybe it takes 1 millisecond, or 10, or 1,000, or 2 microseconds. In this model, we're not worried about the actual timing, okay? It's just a sequence. But you can see that the actual speed of a processor is determined by how long the comp events take. But we're not worried, we're not modeling it. In fact, in this model, we don't care about the actual speed, okay? You see, so this is actually an interesting properties of the model. Huh? So the model separates very cleanly the determinism and the non-determinism. So the nodes are purely deterministic, and all the non-determinism comes in the order of the events, okay, here. And especially in when are the del events happening, okay? There's no notion of speed, and so all non-determinism is in the sketch. Okay, so that's something that's interesting to know, okay? Okay. So, given the initial configuration, so C0, if you know the schedule, you know everything, okay? So the schedule actually gives you everything. You don't really have to even keep track of these other configurations. It's kind of a theoretical point, huh? Okay? Also, there's some constraint in how you make the schedule, huh? Not all schedules are allowed for an initial configuration. So if I start with C0, I can only do a del if there is an M in the outbuff of I in the initial configuration, or in the previous, So I can't do everything anytime I want. So there's some constraints on how I arrange these things. I cannot do a del anytime I want. There has to be a message in the outbuff, clearly. Okay, so there's some constraint there. Okay, and then there's the notion of admissible execution. So this is maybe the most important, this and causality. So this one is important, and you already know this actually. It's exactly the same as fairness in a concurrent system, okay? So concurrent system with multiple threads, you know it has to be fair. You know what that means, right? Right? You remember, what fairness is, without me reading the slides, You know what it means? Can someone tell me? What does it mean that a concurrent system is fair?
No thread will wait infinitely to be scheduled.
Yeah, no thread will wait indefinitely. So all threads that are runnable will eventually get executed. So every thread that can run will run. That's reasonable. You cannot cause a thread to starve. So admissible is the same idea, but for a distributed system. So it's just a little bit more than fairness, okay? So it actually, because now there's a network. In a system of multiple threads, there's no network. You have shared memory. The threads see shared memory, there's no network. But here you have messages being sent. So admissible is fairness plus a second thing. So fairness means each process has an infinite number of comps. So this is thread fairness in a concurrent system. But also, every message M, which is sent, is eventually delivered. The messages cannot stick around, hang in the network forever. That's reasonable, huh? The message cannot just go on the network and never be delivered. All messages sent are eventually delivered. Otherwise, it's kind of like starvation, huh? You're loading the network, and the network is holding on these messages, and it's never delivering them. So admissible executions, they don't allow that, okay? Now, this is actually another interesting point here, a little bit mathematical point. Why do we say a process has an infinite number of comp? Why don't we just say the process runs until the end of the algorithm and then it stops? And then there's no more. Actually, it's simpler to say that all executions are infinite. Why is it simpler? Because if they're infinite, then the messages can wait arbitrarily long times. So there's no arbitrary end somehow. Huh? So when the algorithm is finished, then there's only dummy transitions. So basically, it's like doing no-ups all the time, each process when the algorithm is done. Huh? But the messages are allowed to wait a long time. So it's not because the process is finished that the messages have to be delivered. Huh? So if the computation takes 5 seconds, this is an asynchronous system. Maybe the messages take longer. Okay, there's no arbitrary limit on the messages. So if we do like this, then it means there's no limit on how long the messages can take. Okay, because they can wait arbitrarily long finite times. So this is a pure asynchronous system. So this model is doing the asynchronous model from what I mentioned last week, which is actually the simplest one to define. Because this, what I now define, is asynchronous. But if I want to define it synchronous, I have to add something. Okay? So what I've defined here is asynchronous. An asynchronous system is one that obeys this model. Okay, that's an asynchronous system. That's the formal definition. But I can also define a synchronous system. Remember, I told you what it was last week, is that there is a bound on the message time and a bound on the computation, and the bounds are known. Okay? So in a synchronous system, all the nodes are actually following the same clock. They all execute in lockstep, like soldiers that are all stepping ahead at the same time. And it's a global time, maybe every 10 milliseconds, 10, 20, 30. So there's a lockstep execution, and in each round, maybe it's like 10 millisecond round, every process can send a message. All messages are delivered, which means they all take like 10 milliseconds or less. And every process will do its computation. That means all computations also take 10 milliseconds or less. Okay? So this is a synchronous system where the whole system executes in lockstep. And usually this is called rounds, like in a boxing match, rounds, okay? First round, second round, third. First round is everybody does 10 milliseconds. Everybody is allowed to send and deliver one message. Everybody can do one comp event. That's round 1, and then round 2, and then round 3. You can see the dells here. They're guaranteed to arrive. When I send them, they will arrive in the next round, guaranteed, because all messages are delivered, okay? So there's a bound here. So this is a synchronous system. So in the model, okay, it's basically a constraint on the kinds of executions. Okay, the way to define a synchronous system is we start from this model, which is very free model. The dells can happen anytime, and we add like a constraint on it. We say the dells have to obey an extra rule. So basically we add extra rules to make it synchronous. Okay? So basically we separate the execution into rounds. So rounds is just partitioning the execution. So it's something like this. I have a schedule, E1, E2, E3. So the rounds is we basically make partitions, and we say in each of these partitions, so this is round 1, round 2, round 3, and then there's a certain set of rules of what is supposed to happen in here. Okay? Okay, that means a delivery event for every message in all outbuffs. So if there's a message in an outbuff here, it's delivered in the round. So that's bounded time. Huh? One computation event on every process. So every process does a computation step here. Okay? So this is maybe more than two. Huh? It can be a whole bunch of them. Huh? If there's 100 processes, there might be 100 comp events in round one, plus a bunch of delivery events. And that's round one. Okay? So the DELs cannot wait forever. Huh? And each process is advancing all the time. Okay? So you cannot delay a comp event on one process forever either. Okay? Okay? And in this model, actually, every execution is admissible. Because we're never starving, huh? We're doing everything in every round. So there's actually no starvation here. Huh? Okay? So you see how it works, huh? We add extra constraints. So we have our asynchronous model, and which is very free. And in order to make it synchronous, we add some of these executions are not allowed anymore. The ones where the DELs are taking longer and longer, they're not allowed. We add some extra rules, extra constraints, and we restrict the allowable executions, okay? Only a subset of the executions are allowed. And that makes our model synchronous, okay? So you can see with this model, we can define both asynchronous and synchronous, okay? See that? That's just a mathematical idea. We start with a very free model and we're adding constraints. So synchronous model is in some sense a more restricted model. There are fewer possible executions in a synchronous model. Huh? Executions where the DELs are taking very long are not allowed anymore, okay, in the model. Okay, okay, great. Now let's talk about the second most important concept after admissible executions, which is causality. Causality. So philosophers have a lot to say about causality. Huh? If you ever read Aristotle, has anyone ever read Aristotle here? He introduces many different kinds of causality, and that was a long time ago. Huh? Very smart guy. So we're not interested in things like final causality. Huh? Final causality is goal-oriented. It means that things happen because there's a final goal. It means that everything I do is determined by the fact that in 10 years I will become president of the world. Okay? Well, that's a kind of causality that we're not going to talk about. We're going to talk about a very simple kind of causality where events are somehow determined or allowed by previous events. Okay? So let's talk about causality. And we're going to take the causal relations. We're going to talk about relations between events. And we already know events, huh? Comp events and DEL events. And there's two kinds of relations between events. Events can be concurrent, or they can be causally connected. So concurrent means that there's no connection between the events. Each one can happen before or after the other. Doesn't make any difference. So here's an example of an execution where we have two concurrent events. So here I go from C0, I do comp 1, which gets me to C1. I do comp 2, gets me to C2. Now, you know, I can switch these. I can do C0 and then do comp 2, which gets me to another configuration, C1 prime, and comp 1. And at the end I get the same. You see why that is like that? It's very intuitive, huh? I have two processors, each one doing computation. Well, either the first one does its step and then the second one, or the second one, and then the first one. So those two events are independent. Doesn't matter which one is done in which order, right? You see that? It's very simple, right? So these two events, comp1 and comp2, are called concurrent because I can flip them around in the execution and it doesn't affect anything. You see that? That's interesting. They're independent events. So you can make a picture of that. So here I have two processes. So here I have a comp1, and then I have comp2. But I could also do them in the other order. It doesn't make any difference, of course. I could first do comp2, and then comp1. Doesn't make any difference, right? Because at the end, you end up at the same place. You're going to the same place in two different ways. You see that? It's funny, huh? Here's another example with del's. So I start with C0. I deliver from 1 to 2, a message M. And then I have C1, and then I deliver from 2 to 3, message M prime. Okay? Now, I can flip these too, also. Why can I flip these? Because del 1, 2 is only doing one thing. It's moving message from 1 to 2. Okay? And if there's already a message in 2, it's not removing it, huh? So that this message, when I'm moving here, M prime, is already there at C0, huh? See that? So I could do this one. Oh, sorry, this has to be an M prime. So that's a bug. This has to be M. I did this slide today, so that's my excuse. So the del 2, 3, M prime could be done first. You see that, huh? Because the del 1, 2 is not doing anything to M prime. So that means the M prime and the M's already are there at C0. Huh? That means I can flip those two, and at the end, I've transferred two messages. So I end up in the same configuration. So these two del events can be switched, huh? You see that, huh? Right? You look at what the del is doing, they're not interfering with each other, huh? So you can make a picture also, huh, with that, huh? So this one is, we have three processes. So del 1, 2 is moving a message from 1 to 2. Del 2, 3 is doing this, but you could also do this, huh? Because the messages are already, this transfer is not changing the out buff here, huh? So you can do it like in this order as well, huh? You see that, huh? So the order of two applicable comp or del events is irrelevant in an execution. We say that the events are concurrent. Okay? So these two events are concurrent, and these two events are concurrent. Right? Concurrent, basically it means they're independent. We don't care about the order. There's no connection between them. Okay? You see that? Okay, now I want to show you a case where there is a connection. So here's a case where there is a connection. I have a del and a comp. So here's a del, moving M from out buff 1 to in buff 2. And here's a comp on 2. But the comp on 2 uses the M in buff 2, which was put there by this one. So you cannot flip these two, because comp 2 is using something from the del 1, 2. They cannot be switched. You see that? It's clear why not. There's a connection between them. One of the events is using a result of the previous one. So we say that the two events are causally related. So del 1, 2 is causally before comp 2. So this is causality. Causality means that the two events are causally connected if you cannot flip them, if the second one needs something that the first one does. That's very reasonable, right? As causality, huh? What do you think? It's very intuitive, right? So you can define an order between all events now. Here I just show you a few. But if you look at an execution, here a schedule, for example, you have huge number of events. Huh? You could define any two events, EI, EJ. You can ask yourself, are these two events causally related or are they concurrent? Who knows? Maybe they're causally related, maybe they're concurrent. And you can define an order, a partial order, among all the events. You see that, huh? So this is the definition. So this is a super important definition. A lot of reasoning in distributed systems based on this. So we look at all the events in an execution or schedule, and we define, this is called happens before. So it's a less than with an H, okay? And you read it happens before, okay? If A occurs before B on the same process, then A happens before B. If A produces an M, okay, it puts an M in the outbuff, and B delivers that M, then A happens before B. Absolutely. If A delivers M, and B consumes M, so it basically reads the inbuff, okay, then A happens before B, okay? So in the first case, these could, for example, be two comp events. The first comp event goes from state S1 to S2, and the second one goes from S2 to S3. You cannot switch them normally, yeah? Sometimes you can if it's incrementing by one, but usually you cannot. Computations have to be done in the right order, huh? You can't just randomly mix the instructions of a program. It won't work anymore. So this is basically sequencing on the same process. And these two are for delivery. If I send something, so here the produce, and somebody else delivers it, then the delivery has to be after the send. Okay, that's clear, right? And here it's the other side. If a message is received, and then I do a computation with that message, computation has to be after. See that? And then there's a final rule, which is transitivity. If A happens before B and B happens before C, then A happens before C. So this is what makes it very interesting. You can actually have sequences of events, any two events. They might be far away from each other. They may be still causally connected. And it means that C somehow depends on A. Maybe A is sending a message from 1 to 2, then there's a computation, it sends a message to 3, does a computation, sends a message to 4, and does computation. So that computation depends on the whole chain, clearly, So that's what this rule is telling us, okay? So this is important. In a distributed system, that's all you really know, is the causality, okay, between events. So, and two events are concurrent if A is not happening before B, and B is not happening before A. So anything that is not covered by one of these cases is concurrent, and it's written using the two parallel lines. So A and B are concurrent. Okay, A is concurrent with B. So this is a partial order. You remember the difference in the partial and the total order. So a partial order means that there's not necessarily a connection between all pairs. Integers are totally ordered, because every integer will be less than another, or greater than, okay, or equal. Whereas here you can actually have two events that have no connection. Okay, so here's a picture to show you. So this is a kind of picture we're going to use a lot. This is called a time-space diagram. It has nothing to do with relativity theory, okay? Because we're assuming global time here. If you want to do distributed systems and make them relativistic, then it gets more complicated. People have thought about that, but I'm not going to present that here. And in most cases, it doesn't make any difference. Okay? The Earth is not big enough for it to really make a difference. Okay? So here we have three processes, and time goes from left to right. And each of these things is an event. So this little thing is a comp event. It's purely local. Okay? Here, it's a message being sent. So basically, the beginning of the arrow is a comp event that puts something in the out buff, and the end of the arrow is a del. Okay? But it looks like there's a message being sent. So here I put it in the out buff, and here I'm taking it out. I'm moving it to the in buff. Okay? And then this del could be much later. Huh? So events that are sequencing on the same process are causally related. Okay? So this one, for example, it puts something in the out buff, but that comes from here, that thing coming in the out buff. Okay? And this thing also will remove a message. Okay, now this will put in something in the out buff, but it will change the state. So this also depends on that. So these are all causally connected, whereas these two are concurrent. You see that? So you can look at all these events. So each of these beginning and end of arrow here, these things, they're all events. Huh? And there's a global sequence because it's an execution. So the first event, the second, the third, the fourth. So these vertical dotted lines is like a global time. And so this actually corresponds to an execution in the notation we have. We have E1, E2, E3, E4, and so on. So some of these events are causally related and some are not. Okay? So for example, this one and this one. What do you think? You tell me, are they causally connected or not? What do you say?
No.
No, why not?
Because the step in P3, we don't have any constraints on when it happens.
Yeah, okay. You can say, there's different ways to say. You can say there's no causal chain between them, according to our definition, okay? You can also switch them. You can put this one here and this one here, and it will not change the final result. So they're concurrent, huh? Okay. Okay, so that's reasonable, huh? You getting? You see causality? Now I'm going to say something a little more subtle. Okay? I'm going to talk about similarity, and then I'll tell you what it means, what the intuition is. And this is a very strong intuition. Okay? So I have an execution of a distributed system on many nodes. Okay? P1, from P1 to Pn. And there's events here. On all these nodes, there's events. There might be messages, whatever. There's events. The view of Pi in E, denoted E bar Pi, so the view of Pi is the subsequence of execution E restricted to events and state of Pi. Okay? So basically I have an execution, which is the whole thing, but I'm sitting on Pi. I will only see a subset of these events, right? I will only see these, I will not see all the other ones. That is the view, okay? It's the event and state of Pi. So essentially, the most important part of that is the events. So if I'm sitting on a node, like on this node, and I have a big distributed system, Facebook, millions of nodes are talking, in this node I will only see a small piece of that. That's the view that I have. Now you can do something very interesting. You could say two executions are similar with respect to Pi if they have the same view of Pi. That means on Pi, if I'm sitting at Pi, I cannot tell the difference between E and F. There might be all kinds of stuff happening. So basically this part is the same, but this part is different. Okay? See that? They're similar with respect to Pi. And now the final step, two executions are similar if they're similar with respect to every node. Now we get to something very interesting. We have an execution which looks the same at every node. Okay? I'm sitting on P1, I'm sitting on P2, I'm sitting on all these nodes, and it looks exactly the same. I have two executions, and they both look exactly the same. Are they the same, or can they still be different? That's interesting, right? How are they connected? This E and F, they look the same with respect to every node. Okay? Actually, we can say something very interesting now. So we can say something very interesting. There's a theorem that we can say. So the connection between E and F, actually, the connection is related to causal order. So if we have two E and F that look exactly the same to all the nodes, that means as far as the nodes are concerned, they're doing the same thing. Huh? They will get the same result, of course, huh? Because each node sees the same. But maybe there's still a difference in how the messages are sent. So how could they still be different? Actually, they can still be different, even if the result is exactly the same. And this is the theorem. Okay, so assume E is some execution, okay, and V is a schedule. So these are all the events. Okay, this is an actual execution, E, for example. Now, let's make a permutation of these events, but we preserve the causal order. So we permute. So each of these, so this is a million, this is infinite sequence. Huh? Here we're permuting. So each of these F's, F1, F2, F3, is actually one of the E's. Huh? We don't know which one, it depends on the permutation. So F1 might be E3, F2 might be E1, and so on. It's the permutation. Okay? But the permutation preserves causal order. So what does that mean, it preserves causal order? Well, we say this. If Fi happens before Fj, then in E, I is actually before j. Okay? That means we're not flipping time, in fact. Huh? If Fj depends on Fi, so if Fi happens before Fj, that means that this happens before relation is coming from here. Huh? That means that there's a causal connection between the two, causality, like in the real world. Huh? Well, that means that I will actually be before j. That means we're not traveling backwards in time. Huh? That's what it means. Huh? If I would be greater than j, then it's like we're traveling backwards in time. No, I will be less than j, so that means time is still going forwards. So basically we're flipping the events around, but time is still going forwards. Okay? Now, if we do that, so we permute them anyway, then E will be similar to the execution with schedule P. So we actually do not change anything. As long as we respect causality, we're not changing the result. Okay? So I have to show you some pictures now. So this hopefully will give you some intuition on this. Okay? Here we have 3 executions. These 3 executions are similar. That means if you look at P1, then it looks the same on all 3. If you look at P2, it looks the same on all 3. And if you look at P3, it looks the same also. Now, there are some causal connections here. So they're similar, which means that executions, and it turns out that they're doing the same work, of course, because each node is doing the same thing, okay? But you can see how they differ, huh? You can see, for example, the concurrent events, we can flip them around, huh? But the causally related events, they have to stay in the same order. So here, for example, this pink one has to be before this pink one, pink, pink. So this pink chain has to be still there in the same order, right? The pink chain here, huh? But some of the other ones, we can flip them. Like this one is clearly concurrent. We can move it back and forth. Okay? So that means that similar executions, even though the messages are traveling differently, are actually doing exactly the same thing. Okay, so this is the example of 3 similar executions. Huh? Okay, and there's many of them. Huh? As long as causal order is preserved, they're similar. Okay. Okay. If 2 executions have the same set of events and causal order is preserved, then the 2 are similar. Okay, and they could have different permutations. So as long as causality is preserved, they're similar. But what does that mean also? So mathematically, we can actually say that similar executions form an equivalence class. So if I run the same program many times, and it does the same thing every time, same causality, the messages can still be going differently. It's always doing the same thing. Okay? So similar executions are doing the same thing. So the thing that they're doing is called a computation. So all these similar execution is actually the same computation. Okay? So an equivalence class of execution is called a computation. And the connection is causality. Okay? If you move the message around while you respect causality, you're not changing the result. So the same computation holds. Okay? So causality is super important, actually. Yeah? Okay. So this is an important thing, but I'm sure that I have not given you all the intuition yet on this. There's a lot more intuition I can give you, but now is not the time because it's 6:15. But now I would like you to meditate this, and next time I will give you more intuition. So hopefully, by doing it in 2 steps, next week with some more intuition, that you'll get it.